Visualize waking up in the morning midsummer. You're probably imagining a little light streaming through your bedroom window as you open your eyes while hearing birds chirping and maybe the occasional kid on their bike. It sounds pretty nice, right? Well, that's not how it is for people all over the globe and even some close to home. They wake up, take a deep breath, only to inhale dangerous toxins. There are no birds because of the severity of the pollution, and there are certainly no children outside. Areas like these are chemical danger zones. I'm one of your hosts, Bella, and today we will discuss the dangers of chemical danger zones.
Hi, I'm Emma, your second host.
And I'm Sean, the third host.
To understand the dangers of chemical danger zones, we need to know how they're created.
Chemical danger zones are easy to form. Typically, when you hear something described as a chemical danger zone, you must think it has to come from some sort of freak accident, such as a power plant explosion, which can cause chemical danger zone, but that typically is not the answer. The cause is most likely less extreme, such as factory gas leaks, factories disposing of waste, train accidents, and even certain chemicals are in your home. For example, if you mix bleach and Windex, you can create mustard gas, turning your home into a chemical danger zone. Chemical danger zone simply means that dangerous chemicals have been leaked into the air.
Now that we know what a chemical danger zone is, how can we identify it?
You can easily Google if there are chemical danger zones near you. I'm sure you think there probably aren't any near you because you and the people you know aren't directly experiencing the effects of one, but that's what we thought too. Only to find out the dump on Lee's Lane has over 400 drums of toxic chemicals.
But what kinds of chemicals can be released into the air?
There are tons of chemicals that can get into the air that would negatively impact those near it. But the more common chemicals you'll find are butadiene, hydrogen fluorine, sodium hydroxide, ammonium nitrate, coal ash, arsenic, cadmium, lead, vanadium, and chromium.
So now we know what can cause a chemical danger zone and what chemicals are often present within one. But what do we do if we're in one?
The only way to prevent a disease is to immediately leave the area. If you realize you are in a chemical danger zone and you choose to stay, you may have seizures, respiratory issues, shortness of breath, nausea, dizziness, irritation to the nose, eyes, and throat, cancer, and sometimes even death. Now that we know about the internal effects of chemical danger zones, let's look at the internal ones. How these toxic chemicals are made, chemical bonding.
Chemical bonding is an interaction between atoms, ions, or molecules. There are two main types of bonds, covalent and ionic. The main difference between them is how they're formed. Covalent bonds are formed between two nonmetals, and both of their electrons are attracted to each other, keeping the atoms close. They don't touch all the way because of the protons in the middle repelling each other. An ionic bond is created by a metal and a nonmetal when the metal gives the nonmetal electrons, making the metal positively charged and the nonmetal negatively charged. This brings the atoms closer together.
So, can atoms have multiple bonds with each other or with other atoms?
Yes, atoms can have multiple bonds with different atoms, and atoms can also have multiple bonds with the same atoms. However, there are different kinds of bonds. If two atoms are formed and make two bonds together, they will be called a double bond. If they have three bonds, it's a triple bond. The more bonds, the stronger the compound is.
So why does it matter if an atom is strong and stable versus weak and unstable?
Strong and more stable bonds are harder to break, while weaker and less stable bonds are easy to break. Ionic bonds have the strongest chemical bond because of the process creating an ionic bond includes a complete transfer of electrons, making the bond more difficult to break.
You know there are two types of covalent bonds, polar and nonpolar bonds? Nonpolar covalent bonds are the weaker, and polar covalent bonds land in the middle.
What does polar and nonpolar mean? And how do we know the difference between the two?
We can tell the difference between polar bonds and nonpolar bonds because polar bonds are symmetrical. Not only that, but the polar bonds' electron distribution and electronegativity have to be greater than 0.5, which is good since polar bonds and nonpolar bonds can't mix.
Okay, so I understand that polar bonds have to be asymmetrical. But what is electronegativity, and how is that measured?
Electronegativity is how likely an atom is to attract and share electrons. It's measured by where it is placed on the periodic table. Electronegativity is the least on the left and increases while going right. Electronegativity also increases as you go up the periodic table. So the ones on the top right have the most, and the ones on the bottom left have the least.
Is there anything else we can tell based on the placements of the periodic table?
Yeah, there is. We can also count valence electrons based on where the element is on the periodic table. Whatever column number the element is in, that's how many valence electrons that element has. However, with columns in the double digits, such as 11, 12, and 13, you drop the 1. However, there's an exception. Helium only has 2 valence electrons, even though it is in the 18th column.
Why are valence electrons different from normal electrons? And why would helium be placed in the 18th column if it only has 2 valence electrons?
Valence electrons differ from normal electrons since they go around the atom in a series of shells, versus normal electrons that just stay on the outside of the nucleus in the first shell. The first shell will also have 2 electrons, but any other shell can hold up to 8 valence electrons. And, if you couldn't tell yet, how filled the atom's outer shell is determines which column it goes into, meaning helium is in the 18th column because its outer shell is filled.
Any atom can only have as many electrons as they do protons. And since helium only has 2 protons, it can only have 2 electrons. This combined with the fact that the first shell can only hold 2 electrons to begin with, that means that helium has completed its outer shell like the other elements in this column. However, since the other elements in that column have more protons, they each need a different number of electrons to fill their shells. But unlike the rest of the elements on the periodic table, they have successfully filled out their shells.
That's all great information, but how does this all relate to chemical danger zones?
All that information relates to how we react to chemical danger zones. As Sean mentioned earlier, that polar and nonpolar bonds can't mix. One common example of this is water and oil. That doesn't sound like a big deal, but in a chemical danger zone, this can be a real threat. For example, as I said earlier, one of the most common chemicals in a chemical danger zone is butadiene, which is not only very flammable, but nonpolar. And since water is polar, you can't put out a fire with butadiene using water.
Another example of when it matters if something is polar or nonpolar is if a chemical ends up in waterways. As Emma said, water is polar, meaning that polar chemicals can mix with that water, turning that water poisonous. But nonpolar chemicals just sit on top of the water, which is less of a concern for human consumption and more of an issue for any surrounding wildlife. But we've talked a lot about polar and nonpolar chemicals. Another factor is how strong the bonds of a chemical are. This is important because it directly affects if they can transport a chemical out of a chemical danger zone. Strong bonds are more difficult to break than weaker bonds. This means chemicals with weak bonds probably can't be transported because of the increased likelihood of a chemical reaction occurring.
So what do you guys think we can do to help fix this issue?
Well, I personally think a good place to start would be to look up if there are any chemical danger zones near you and look up corresponding cleanup companies in your area to donate to. One good example for us is the Toxic Release Inventory Program.
I think that's a great idea, Emma. I also think that spreading the word to your friends and family about what a chemical danger zone is, and if there are any near you, keeps you and your loved ones safe and informed.
I think those are great ideas. Another organization you can check out is Clean Earth. I also think checking to see if there are any petitions or fundraisers to help clean a chemical danger zone near you would be helpful.
Great, now that we have some ideas, I think it's time to spread the word. And to help us better spread the word, there is a quick survey attached to this podcast that helps us improve what we are talking about based on your input. It will just ask a few simple questions on how well we explain this topic. It would mean a lot to all of us here if you took a few minutes out of your day to fill it out. But with that, this is the end of our podcast. Thank you all for listening.